I love that. Let's just say that again. Entanglement is a fuel for quantum computations. I'm going to put that on a t-shirt or something. That's great. Hey everyone, welcome back to the fAQ podcast. I'm Tai-Danae and I'm here with Adam today. Hey Adam.
Hey Tai-Danae, great to be here with you again. And you know, Tai-Danae, these last couple of episodes, we've been talking a lot about concepts. We talked about qubits, we talked about superposition, we had an awesome conversation about entanglement. And I think that it might be kind of nice to talk a little bit about applied quantum technologies for an episode or two to kind of take some of those concepts, firm them up, make them feel a little bit more concrete in the framework of how you can use those concepts to actually build things. What do you think?
Yeah, absolutely. I think that's a great idea. I mean, especially when you're first learning, like you mentioned, those three words that we focused on, qubits, superposition, entanglement. I mean, first of all, these are not everyday words, that we use in our daily vocabulary. So when you're trying to kind of grasp these ideas, wait a second, what does it mean really? I mean, what's the concept really? I do think that having actual examples, real world applications to kind of hang your hat on would be very helpful. So I like this idea that we're going to intentionally sort of shift gears on the podcast and move from the abstract ideas to more, applications. So one thing though, okay, when we chat about applications of essentially, quantum physics or these basic ideas in quantum physics, maybe one idea that could come to a lot of people's minds immediately are, quantum computers. We're going to talk about quantum computers now. Right? Like this is a very popular thing. If you don't know, if anyone's listening and they don't know what a quantum computer is, then that's totally okay because we have plans to actually talk about that in a future episode, but not
no
quite
spoilers,
yet.
No spoilers, Tai-Danae?
No, I'm sorry. I just let it all out. Yeah. I mean, maybe it's a little bit inevitable. We have a podcast on quantum tech, so eventually we are a little bit obligated to chat about quantum computers, but I think that's not really what we want to do today because the wonderful thing is that there are so many other applications of quantum physics to the real world besides computation. And I think it'd be fun. I mean, we chatted about this, in preparation for this. We think it'd be fun to talk about a different application to start us off. What do you think?
Yeah, no, I think that's great. I like taking that idea that quantum computers is what mostly hops into people's heads and just think about like, okay, that's true, but there are lots of other things out there. And to talk about those things specifically, but even before we get into that, I think that talking about the sort of ecosystem of quantum technology and the ecosystem of different quantum systems can be fun. It's an interesting thing that I sort of started learning about and is kind of inspiring. So I think maybe I'll talk about that for a minute or two, if that's all right. Okay.
Absolutely.
Yeah. So we actually touched on this. I think when we talked about qubits in the first episode, we talked about there's all sorts of different types of qubits that are out there. There's superconducting qubits, quantum dots, all sorts. We talked about NV centers, nitrogen vacancy centers, all sorts of different types of systems. And that's just a handful. There are dozens more. And then for each one of those, there's flavors of dozens of other ones. So I think thinking about that diversity of quantum systems is really interesting. Yeah. And the way that I've kind of interpret that diversity is it's exciting. It's almost a little like the Wild West out there. And I think that it kind of is emblematic of where we are in the development and evolution of quantum technology, that there are so many different systems out there that can be used. That diversity of systems means that we're still on the cutting edge of learning about how these things work. And we're not totally sure about which system might fit best for which application. And certainly there's going to be lots of different systems that get picked depending on the application that that quantum scientists, engineers, and other folks need, like to fit for purpose. They need a system to fit a certain type of application. There's a menu of these different systems out there. More are being discovered relatively frequently. They're all being refined at different rates in different ways. And it's just a really exciting time, I think, to be involved in all of this. And we're going to be talking about some of these different systems today. We've talked about some before, and then in the future, when we talk about quantum computing, we'll talk about other types of systems. I think it's just a really exciting time to be a part of this because people out there that are working on these things right now are making discoveries right now and refining those discoveries for specific applications and products. And as some of those systems get refined, ideas for applications are starting to come out of that side of things, like that we don't know what we don't know. And as we start to understand more about these systems, more and more creativity is going to be involved with creating more applications. And I think that's incredibly exciting. What do you think, Tai-Danae?
Yeah. Oh, you've expressed this so beautifully, Adam. That was a great sort of overview of the landscape, I think. One thing, that would be to kind of bring that point home is to kind of pick one of those discoveries or one of those avenues, and focus on it. And so, I mean, you actually mentioned this, and folks might remember if y'all listen to our first episode on the podcast on bits versus qubits. And you just reminded us, Adam, we did mention very briefly a certain kind of qubit or a physical, representation of this idea of a qubit called an NV center, nitrogen vacancy center, which just kind of as a quick refresher, we just mentioned this very briefly. The idea is that you can start with a material like diamond, which is built out of, carbon atoms, like this nice, very structured array of carbon atoms. And then you can replace a couple of them with a different atom and then kind of work with the physics that you get there and sort of use the laws of nature at that level in this different configuration in your diamond to do different things like sensing. Now, we mentioned that very briefly, and you kind of mentioned it in your overview just now, but this is something that would be very valuable to discuss in depth. This is actually an application that's being used right now in the real world by really, really smart people. So I think it would be great to focus on that, NV centers, in today's episode.
Yeah. I think that's great. And I think just talking about sensing is really interesting. It's not something that I knew about when I first learned about quantum technology. Right. And I wish I remembered this person's name. You might remember, but there's a scientist out there that also is a really great science communicator and talks about quantum and is also very anti-hype. And I know we're very anti-hype here. And I remember reading something from her where she talked about like the more you hear about a particular quantum technology, probably the hypier it is. So when you start hearing about quantum computers solving all possible problems, if that's all over the news, it's probably not true. But the opposite is also true, that the types of quantum technology that you hear the least about is probably the least hypey and the most like far along. And sensing, I think, is one of those things where quantum sensing has been around for a while. It's now getting refined with new technology and lots of creativity from engineers. And this is happening now. It's much more advanced in certain ways than quantum computing, for example. So I think that's a great place to start today, to kind of let people know that these things are real. They've been around for a while. They're getting better and better. And the applications, we're just sort of starting to get into the different applications of some of these quantum sensors.
Yeah, excellent. I love that. This is going to be our hypometer. How much are we hearing about this idea in the popular media? But yeah, let's shine some light on this.
Let's see what you did there.
Let's shine some light on today's, application of the day in vCenters. And I think it's a great time to bring on an expert. What do you think?
Let's do it.
So today we're very happy to have Stefan Bogdanovic with us on the podcast. He is a senior research scientist at SandboxAQ and the founding member of our quantum sensing team. So hey, Stefan, it's nice to have you.
Absolutely. Thanks for having me.
Thanks, Stefan. Before we get going, I think it'd be really interesting to talk a little bit about your academic background, if you could, and what you were doing right before you joined SandboxAQ.
Yeah, absolutely. I come from Serbia, where I did my undergrad in Belgrade. I was a theoretical physicist by my background, but after which there was a switch towards experimental science. I went to the Netherlands for grad school. I did my PhD in the group of Professor Hansen at University of Delft, where I was first exposed to quantum information theory and experiments as well. It's where I learned what a qubit is, how to manipulate it, how to create it. So even before that, I was more theoretically, this was more on the applied side as well. So there I use this particular defect in diamond, which is called nitrogen vacancy center in diamond, which we actually covered in one of the previous episodes, and did some experiments with them showing their utility for some advanced quantum technologies like quantum networks in particular. Following this, and we can, of course, dive deeper throughout this conversation in the details of that. Following this, I did my postdoc at Harvard at a group of Professor Marco Lonchar, using similar defects, although now based on silicon vacancy centers. The defects are many in diamond. They come in all shapes and colors as well. And these are they have also used utility for quantum networks, although with a different twist or a different spin on them. So following this, at the end of 2019, as I was wrapping up my postdoc, I wasn't really sure what I'm going to do with my life when it comes to academia or industry. And then a call came from this super high secret clandestine team at Google at the time called Sandbox to join and start the quantum sensing efforts using some of the technologies I've been working on during my grad school and my academic work. So I joined since 2019 and start developing quantum sensing efforts, starting with NV centers, but then going forward looking at other sensors as well. And we'll touch on a couple of them. This is just to show that when you learn one platform in quantum technology, they can be useful for multiple things. Things you previously considered that will be used only for, let's say, sending information far, can also be used to sense some things that are very nearby as well. It's a very ubiquitous technology in general, like quantum tech.
That's. Oh, go ahead, Adam.
No,
go
ahead. No, that's fascinating, and I didn't even know that you had worked on quantum networks before. So I think that's something that I don't know if you agree, Tai-Danae, that we should probably have Stefan back forward to talk more about that. What do you think?
Absolutely. I mean, that was fascinating, Stefan, your background and how you ended up at Sandbox. So there was a lot there, and I want to get to especially NV centers. I mean, Adam and I were chatting about this earlier, and as you mentioned, we brought NV centers up briefly in one of our earlier episodes on qubits. So maybe since you are the expert, you can, kind of check our understanding here. Can you tell us and tell our listeners what an NV center is? I mean, nitrogen vacancy center. You mentioned the word diamond. Is it like, do we buy these at the jewelry store? Like, what is this thing?
Yeah, absolutely. Although you did such a great job in the episode 1, I can even pull the notes and read them back to you. It was excellent. I'll just try to provide more depth and a little bit more flavor. Also, maybe just to start as a caveat, to make this more accessible, I will have to dial down on some scientific rigor. Yeah. So if there is maybe an expert in the audience listening to this, just bear with me a bit. I'll try to just kind of stay away from some deeply technical descriptions. So I guess diamonds are when the natural diamonds that you can find in Earth that you can mine and that you can sell for jewelry sometimes come with different colors. And the reason for this is not because of something that a diamond lattice that consists of carbon brings. They're usually transparent. But if there's any impurity in a diamond lattice, like with boron or with nitrogen, diamonds can have a different color, like yellow or brown or blue. So in a way, the colored diamonds have existed with defects, have existed for a long while now. And all of these different defects have different properties. Nitrogen vacancy center is one such defect, but it's one in the line of many. There has been an encyclopedia of diamond defects, sometimes in the 70s, with thousands of them, I think. Each of these defects has a different property, but all of them really come as this really a twist in the diamond lattice. Or you try to take pieces of the diamond lattice, which is basically a lattice of regularly spaced carbons, and you take carbon atoms and you replace them with a certain other atomic species. For NV centers, these two carbon atoms that are adjacent and they form a bond between each other are replaced with a nitrogen and then adjacent vacancy, so an empty spot. And this complex inside the diamond lattice is called the nitrogen vacancy center. Now, why are they so useful, and why did they become so interesting for us? Well, it's this type of kind of bond or this type of complex inside a diamond lattice is almost like a trapped molecule inside it. So basically, diamond lattice freezes and kind of shields this molecule within it, and it basically creates a perfect housing for this defect to exist. Diamond is hard; it's also transparent, so it has a lot of important properties to house this defect if you want to really probe its quantum properties.
So just to kind of recap, I mean, this is clear from what you said, but I just want to make it, explicit.
Hmm.
When you say a defect in diamond, maybe the layperson might think like, oh, I scuffed my diamond ring, or I like,
Hmm.
banged it on the countertop or something. But that's not what you mean. You mean like a defect at the molecular level, in
Exactly.
particular,
It's a molecular defect.
yeah, some type of,
Yeah.
irregularity in the atomic structure.
Yeah.
Yeah.
Exactly.
Yeah,
So, and then,
and
go ahead. Sorry.
no, yeah, no, thank you. Before you move on, and you mentioned that these defects have been known for a long time. They are sometimes natural, and you can find them in different colored diamonds. Can you talk a little bit about these nitrogen vacancy centers that you might use or that we use at SandboxAQ? Are those mined? Are they found in the ground? Are they created in a lab? I know you can buy lab-created diamonds at the jewelry store and things like that. So without going into too much detail, maybe
Yeah.
like where do these things actually come from that are useful in the lab setting?
Absolutely. So these, although they started, the field of probing optical properties of defects started using natural diamonds, ever since we really evolved and started using lab-grown diamonds with implanted or grown defects in a specific way. There's a different way how you can produce them, but you really need to go to the lab and you start building this diamond lattice, almost like an atomic Lego. You start with a small diamond, and then you start putting a carbon atom and a carbon atom, and you start growing this Lego of carbon atoms to create bigger and bigger diamond. And let's say at some point during this Lego process, you introduce a different atomic species, like a nitrogen, it will start incorporating into this diamond lattice that you can then top off with more carbon or do whatever you want. And that is one way to grow it, basically. You grow it basically layer by layer, atom by atom, by introducing different species, and they will kind of combine each other to kind of conform to this diamond lattice. There are other ways you can do it as well. You can implant these nitrogen atoms. You take a pure diamond and then you bullseye just kind of with an ion gun or with a certain kind of implantation method. You can bullseye these atoms at different places. If you want a really particular accurate location of these defects, then you have to do it like this, because then it's a really down to nanometer, or let's say maybe less than a microscopic scale implantation accuracy is needed.
Wow. And so that brings up an interesting question. So when I first started thinking about nitrogen vacancy centers, in my imagination, I thought of like basically a pure diamond with that one spot of a replacement of two carbons basically coming out, one of them being replaced with a nitrogen. And then there's just that one NV center in the middle of this perfect diamond. And then we can use that in the lab in ways that hopefully we'll get to talk about soon. Is that accurate? Like, is there just one? Do you usually just have one nitrogen vacancy center in a diamond, or can there be more than one? Or does it depend on the application?
It absolutely depends on the application. If you want to use, let's say if you want to use this defect for sensing, and we'll get to how you can do this, then for some applications, it's beneficial if it's many of them together. Let's say an ensemble of them, which can be billions and billions. And then the more you have them, the better your sensing properties are. In some cases, you want to have a single defect, sense a single object, or you want to interface a single of these defects with light, and then send information in this quantum network way. So you will use a single NV center. This is to say that it depends how quantum you want your operation to be. If you really care about quantumness to the level where you care about superposition and entanglement, which I think you covered in your previous lectures. So if you want to utilize this really powerful properties of quantum systems, like all the way to entanglement, then you will use a single one, and you will then entangle it with a single NV center far away in the quantum networks. If you want to boost your sensor, then you will use many of them, plurality of them. You will lose a little bit of quantumness, but then what you will gain is this huge sensitivity improvement.
That's really cool. So I would love to just kind of park there for a little bit. Can we I mean, how does it work? So I even want to understand these two kind of extremes that you mentioned, because it would be really nice to connect this application to some of these fundamental concepts that we've talked about earlier on the podcast, like superposition and entanglement, as you mentioned. But maybe can we talk about the sensing application first? If I have this carbon lattice, I remove one of these carbon atoms, or two of them, and I replace one with a nitrogen. I have this little NV bundle now. How is that used as a sensor?
Yeah. So let's then go very light on quantum before we dig deeper into it. Let's say when we discuss on networks. In very high level, the NV center is a trapped molecule inside a diamond lattice. So you get trapped system for free. Usually you have to go through extreme lengths to trap a quantum system. But here in diamond lattice, you just buy a piece of diamond, and inside of them, there's a billion trapped molecules for free. What
Oh,
they have, yeah, go
can I
ahead.
interrupt you really quick, Stefan, because I think that's like a huge point, and we talked a little bit about that early on when we were talking about qubits. When you say trapped, is that similar to like in a superconducting quantum computer, we have to cool things down really, really cold and shield them to kind of isolate them from their environment? Or in other cases, you use lasers to slow things down and to sort of trap them. So if I hear you correctly, like is the diamond lattice sort of naturally trapping that NV center system in a similar way?
Exactly. It's trapping and isolating them from certain fields from the environment. So you don't need to use the optical trap or a trapped ion or an ion trap for a certain quantum system. You get it for free.
That's very
And
cool. I just want to say
yeah,
that's very cool.
and this is really what kickstarted the whole basically era of NV centers is how easy it is to make a quantum experiment. You need a piece of diamond, you need a laser, you need a detector, a couple of microwaves, and bam, you have a tabletop quantum experiment. You don't need to cool it down. You don't need a particular shielding. You don't need to just like vacuum, like laser trap in vacuum. So it was really user friendly, and this is kind of really reduced the barrier of entry and allowed a lot of physicists to start playing with the system.
Wow. Okay, that's cool. Well, thank you for allowing that like a little interruption there.
Absolutely.
But yeah, let's keep going about how these things actually work as sensors.
Yeah, so you start with a well-defined quantum system, and that's not a given. As I said, you usually need to go through a lot of lengths to isolate your system because they're also very sensitive to the environment. And then what is a qubit? You have a molecule. Basically, it's a trapped electron system, and this trapped electron system has its spin, and spin is a very natural qubit. Qubit, as you discussed before, I guess, is any well-defined quantum two-level system. It can be light that goes in this direction, that direction. It can be light that has a different polarization. It can be certain flux or charge in a superconducting circuit that has two different properties. But a very natural way to think of qubit is really as electron spin. It's maybe one-to-one very easy analog between what it needs to do as a computational object and what it is as a physical object. Let's say as a spin. Is it a physical object? Maybe it's a philosophical question, but it's physically spin. It has a very good mapping to qubit properties when it comes to computing and basically any quantum information. So in this electron spin has a ground state. It has two different spin states, up and down, and this is already your qubit. Two qubit states. One is the qubit state up, and one is the qubit state down.
So can I just ask a clarifying question? So you're saying this NV center, my nitrogen and a vacancy, the actual qubit is like an electron associated to the nitrogen atom. Is that accurate?
I wouldn't say it's associated to the nitrogen atom because it's a molecule. It's a complex of electrons,
Okay.
but this complex together shares this electron spin. Let's say it's a total electron spin one. So because of this, it has a well-defined qubit state.
I see. Okay.
Gotcha. So then the qubit itself is the spin. And so you mentioned that there's two different states, spin up and spin down. That can be sort of analogous on a non-qubit side. So on a bit side, like the ones and zeros. On the qubit side, we have spin up and spin down. So that leads me to two questions so that maybe you can answer at the same time. But that makes me think about superposition because that's kind of one of the superpowers of qubits. So can you talk a little bit about how the NV center works with the concept of superposition in the overall scheme of sensing in this case? And maybe we'll get to quantum networks later on in this conversation.
Okay, let's first establish one more link before we dig into sensing. This is a universal link for anything you want to do with NV centers. And this is that its qubit states are connected to its fluorescence. What this means, maybe in more layman terms, is depending on the state of its electron spin, they will emit less or more light when probed with light. So what this allows you, it allows you to have a very good link between the amount of light the NV center emits and its spin quantum states, which allows you first to read out its quantum state very well, but also in some cases, and maybe we'll discuss in quantum networks, it allows you to entangle this and send this information far away. For sensing, we are not using the second part, but in the first part, it's very important because this is how we measure fields that we sense. Basically, there is a link, there is a way how we can probe the quantum state of the NV center by just measuring the light they emit. And this link is very important.
Interesting. And
So,
yeah, as a biologist, that's a pretty common thing in biology to have fluorescence,
yes,
where you might have a tag or something in a cell, and then you hit that tag with a laser, and it fluoresces at a different wavelength. So it sounds like that's a similar kind of setup that you're getting with the NV center. Is
exactly.
that right?
It's absolutely the same. So you have a quantum system, you hit it with a laser, the NV center absorbs green laser light, and then emits red laser light back. And the properties of this emitted light depend on its quantum state that the NV center is in. So what you have doing this, you have the optical way to read out its quantum state.
Amazing.
Now,
Go ahead, Stefan, please continue.
So now to establish the link with sensing. So how does sensing work? So we established the link between the quantum state and light, but how do we sense things? Well, maybe just to pull back one step back, quantum sensing is very a natural property of quantum systems just because they're so fragile to anything in the environment. That's why it's so difficult to build a quantum computer. We need billions of dollars. We need temperatures colder than outer space. We need incredible amount of shielding just to keep quantum systems unperturbed because they're so easily perturbed by environment. And this really calls out the really a fundamental property of quantum systems is that they're so fragile that they will react to the tiniest, basically, perturbations from the environment. And what's bug for quantum computing is a feature for quantum sensing, because in sensing, we actually open up the quantum systems to this perturbation, and we use this extreme sensitivity to the environment to then probe something coming from this environment. So in this case kind of now to put it in context of NV centers, the electron spin of the NV center is really like the tiniest, most sensitive compass needle that reacts to external magnetic fields. So in the presence of electric fields, there is a certain, the NV center electron can feel the perturbation and then react when exposed to these external magnetic fields. So this establishes now a link between external world and the quantum state. So now I have two links. The external magnetic fields perturb spin. Spin changes the amount of light. So if I measure the amount of light coming from the NV center, I can tell something about the external world. And this is how we do quantum sensing using NV centers.
Wow. Yeah, that's really interesting. And I'm trying to put together a couple things in my head, Stefan.
Okay.
So we talked before about how like this diamond setup is really a great shield. It's a nice trap for the NV center. Mm-hmm. And I think you mentioned before that it even protects that qubit, that quantum space from certain interactions from the outside world. But it sounds like not all interactions, like the magnetic field can get through, and it sounds like optically, like a laser can get through. So what other sorts of things can you use an NV center to sense? Is magnetic fields really the big one, or are there other things that can get through that diamond shield in a way that is useful to measure?
Yeah, that's a great question. So diamond is a very versatile sensor. You can use it to sense temperature, pressure, electric field, magnetic field, all using very similar concepts. They respond a little bit differently, and you can play maybe a different quantum game depending on which sensing modality you want to use, but you can sense all of these fields using NV centers. So magnetic field is perhaps the strongest one you can use. You can sense. It responds maybe the most strongly to magnetic field perturbations, which is why it's such an excellent magnetic field sensor, but there's certainly other things you can use. One big advantage of NV centers is really that you can use a millimeter piece diamond to sense millimeter-sized magnetic fields, or you can use a single molecule to sense an atomic magnetic fields in the proximity. So you can go from a nanometer distance magnetic field sensing to sensing the magnetic field of the whole planet Earth, for example. And this range, let's say, this range of scale is something that NV center does uniquely.
So one thing I was wondering also, because you mentioned when you were telling us a little bit about your research background, you mentioned this word silicon too. So it sounds like diamonds can be used in some applications, but maybe something else could be used in other applications. Is that correct?
So my background is other defects in diamond. Instead of implanting nitrogen, you can implant silicon, tin.
Oh.
You can implant many different defects. And all of them have their pros and cons for certain experiments. If you want to sense magnetic fields, you would do NV center. If you want to make a good quantum memory, you would also use the NV center. But if you want something really bright, something that will emit a lot of light with a specific properties, you will maybe use a different defect. So depending on your application, you will then tailor and choose. And definitely the jury is out there about what is the perfect sensor for some of these applications, let's say for networks. Now, what you said is also true. These defects can also be optical defects, or the defects that can be pinged by a laser light and then respond by emitting light, can be found in other crystals as well and in other materials, including silicon. So there is now not only a zoo of different things you can implant into diamond, there is also a zoo of different substrates you can implant these ions to boost these properties. And I think the rationale of when would you use which defect, it's still being explored, and I think it's a big maybe another big conversation we can have sometimes down the line.
Yeah, that's really exciting. That it kind of sounds like that we're at the early stages of this type of development, this type of revolution in the quantum space.
Yeah, absolutely.
If I can go back a little bit here with the superposition piece, can you, and you covered this a little bit before, but can you, like, maybe in a little bit more detail, talk about how the concept of superposition really impacts NV centers when it comes to sensing, maybe a magnetic field, for example?
Let me first explain how it plays a role in general, just overall without an application, and then we can. Great. And for some applications, this will be crucial. For some, maybe not so much. So you have this. Let's say you have a single NV center. It has two-level ground state, spin up and spin down. And what you can do, these are well-defined ground states. And if you measure this system, as you probably covered in the previous videos, you will force it to basically decide and to project the system in one of these two. But you can also manipulate its state using a very simple microwave field to prepare a superposition between states up and down. So not only does this ground state of electron can have very two well-defined states, it can be a mixture of these states, a superposition basically of these states. So now if I say that if my spin state is up, I will get a photon, a particle of light back. And if my spin state is down, I won't get any light back. Well, if I prepare the NV center in a superposition of up and down, this means that when I measure the amount of light that comes from it, it will be also in a superposition of yes light if my spin state is up and no light if my spin state is down. And this is what is called the spin photon entanglement. So basically you entangle an existence of particle of light that is emitted by the NV center with its quantum state that is supposed to emit this particle of light in a certain state. And this is fantastic because this type of entanglement, because this entanglement from the ground state of the spin is transferred to the particle of light. Light has very notorious property to travel far. So you can use this to send this information, quantum information, basically send this entanglement very far, kilometers away in some cases.
Wow. Now, okay, so I've never heard this before. I want to slow down and let that sink in and digest for a moment. So the one thing that I think about when I think about measuring something that's in superposition is that it kind of has to decide. Yep. Like at that moment when you measure, you might be at a superposition of spin up and spin down, let's say. But my initial thought would be, my instinct would be that if you measure it, then it's going to have to decide, is it spin up or spin down? And what I think I heard you say is that if you measure it sort of indirectly using a laser, that you can actually maintain that superposition state and furthermore, transmit that state or entangle that state with the photon that's now being emitted from that NV center. I'm sure I got something wrong there, but maybe you can correct me.
So, you're absolutely right. Measurement really kind of projects the superposition and kills the uncertainty, right? So you kind of really nail it to one of the two, make it choose in a binary basis. There is no measurement in this until the final state when you want to do entanglement transfer or even quantum teleportation in case, or even if you want to do computing. Until then, you don't measure. So what you do, you ping your system with a laser light, the system in its superposition, it emits light, which is also then transferred, which is entangled with the spin state. And you don't measure it until you really need it to do this operation. So in a way, you can think about it, and I don't know if you discussed it in this way, entanglement is really a fuel for quantum operations. You need to consume one resource of entanglement to do one operation, let's say, of quantum teleportation transfer or some type of computation.
I love that. Let's just say that again. Entanglement is a fuel for quantum computations. I'm going to put that on a t-shirt or something. That's great.
Because it's a resource, right? You have to consume entanglement in order to start projecting your system. And then depending on what is the operation you want to do, you will then start consuming this in a certain sequence.
Yeah. So is this really how? So we haven't talked about quantum teleportation yet on the podcast, but I think maybe we should just devote an episode to it. But
Sure.
is this another application of NV centers? Is sending
Yes,
information from here to there in exactly this entanglement process you described?
exactly. So you will
Mm.
use this property to entangle something solid, something existing, something
Uh-huh.
local to a particle of light that travels down the, let's say, optical fiber, and it can travel far, kilometers. And then on the other side, you can entangle it with maybe another NV center coming from a different direction. So doing an operation on these two light superposed kind of entangled particles, you can entangle two NV centers that are far. I butchered this a little bit just because I want to keep it very high level, but this
Yeah,
is how
yeah.
quantum teleportation works.
Cool.
However, this is, I think we reversed the order a little bit. I said I will talk about first about sensing and then about quantum networks, but we jumped into this very quickly. But I think it just shows that quantum networks are really a great primer and a great uh, uh, example of the full power of quantum technologies, like quantum concepts like superposition and entanglement. Um,
Yeah.
Now going back to sensing,
Yes.
sensing does not use this. There are down the line, let's say, we will need to merge these two concepts. We will need a quantum sensors that use this quantum sensitivity and quantum properties, but also that use this higher concept like superposition and entanglement to boost the sensitivity of things of what we want to sense. There are a few theoretical proposals of how this can be done right now to increase the baseline, the sensitivity of certain telescopes, to improve the imaging. Quantum superposition and entanglement can be used for this. However, this puts a huge amount of requirements on the operational quantum systems, and right now it's unfeasible, and it's really almost stuck at either the theoretical concepts or tabletop experiments. For us, because we are really using a near-term quantum technology like quantum sensors with real-world application, we use some properties of quantum in our quantum sensors, but we don't go to full stack to quantum let's say entanglement, for example.
Hmm. Interesting. So, can you talk a little bit about that application? So, like looking at NV centers as a sensor, can you maybe do one more click down into kind of how that works? And then I already have like 12 questions to ask you after that, so I'll try to hold myself back a little bit.
Absolutely. So I already kind of touched on quantum sensors and why are they so
Mm-hmm.
advantageous, right? Quantum sensors as really something that really uses the power of quantum, or kind of one of the key principles of quantum systems. I also want to say that quantum sensors are being kind of wrapped around in this bucket of new quantum technologies with computing and networking, but it's not really the case. Quantum sensors have been around for decades, like MRI is a quantum sensor, if you will. There many quantum sensors, like atomic clocks, like GPS, these are quantum sensors as well. I think they've been bundled up just because there is now a newly kind of reinvigorated push for quantum technologies. But quantum sensors have been around on the block for a while now. And not only this, they have already proved that they can be really life transforming because of the technologies they have enabled. So there is no, I know for quantum computers and networks, there are questions when they will come, how much infrastructure we need to build them, how really revolutionary they will be. They will likely be, but we still haven't really scratched the surface of what they will do. On the other hand, quantum sensors have been here for a while. They have been tried and tested technology, and now it's really up to us to find more and more applications, but also to make them more accessible. And through this, I think this is now segues into some of the applications that Sandbox and in general that people have been using to really explore and use the full power of sensing. And I can mention a few. For
Yeah, let's go for it.
especially concerning NV centers as magnetic field sensors and as a very sensitive magnetic field sensors with even high resolution and even vector sensing, which is something that doesn't come really often in the sensor world. Basically, and I'll just put this maybe as a footnote, different orientation of these NV centers in a diamond lattice responds differently depending on the direction of the magnetic field that impacts them. So because of this, you can use NV centers as an inherent vector sensor. And this is something that's quite rare in the world of magnetometry, quantum or classical. So at Sandbox, and in general, these things have been used. Like, what are the applications of high performance magnetometers, quantum in particular? One application is and another differentiating factor compared to classical magnetometers is they are self-calibrating. A lot of classical magnetometers, even those with high performance, have to be recalibrated after a certain time. They drift due to certain effects. Quantum sensors' properties are really set by physical constants, laws of nature, so you don't have to recalibrate them. And even you can use quantum sensors to recalibrate some classical sensors in your system. So there's actually a really strong, there's a couple of compelling reasons to use quantum sensing beyond just their inherent sensitivity. Now, once you have this great sensor, what can you use it for? Well, there's a couple of really profound and groundbreaking applications of this high performance magnetometry where quantum sensors can play a role. For example, you can use them to navigate the planet Earth without GPS. So almost like a passive, non-radiative system to improve your navigation. How does it work? Well, each point of Earth has a unique magnetic fingerprint due to its crustal field of the Earth. As Earth cooled, it created magnetic crustal field, and the imperfections or the non-uniformities of this field are unique at each point of the Earth that you can then use to navigate using these high-performance magnetic sensors. And for some cases, this is the only thing you can use if your GPS is unavailable, for example, underground or in other cases. Other groundbreaking application, and this one is very near to and dear to my heart, is measuring the tiniest and faintest magnetic field signals coming from your heart. We know, I think most of us have heard about electrocardiograms measuring electric fields coming from the heart. But if you can resolve magnetic fields coming from the heart, which you should be able to because everything that emits electric field also emits a magnetic field, you would be able to pick out the tiniest magnetic field responses from the nerves firing as your heart operates. And this can be used to tell with greater prediction and also much earlier, is there an adverse event coming, cardiac event coming your way? And is this something that you should need to check out? These are two very kind of groundbreaking and profound applications, but there are many others depending. Let's say if you want to use the extreme spatial resolution of NV centers, basically use a tiny NV center as a molecule, you can bind it to another molecule and use it to do this magnetic fluorescent imaging, something that's very well already established in the scientific literature, fluorescent imaging of certain bioparticles. But now you also have come with this magnetic sensing, which gives another additional advantage. You can also use it to put it in a very tiny, tiny needle and cross over with this needle, almost like a little magnetic microscope that's maybe 10 nanometers large, and use it to probe very local magnetic fields on this very tiniest basically footprint. And this has been used for material research. Actually, you can use it for many, 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 many different applications.
Wow, I love thinking about the scale of use, not only the number of different uses, and I know you've just talked about a few, but everything from like navigating across the globe to these tiny little needles that are assessing attributes of new materials, for example, or like looking at magnetic fields produced by nerves in the heart. Like the scale there is just also very, very impressive.
Nerves of the heart, brain as well, right? You can also use this encephalograms to kind of measure magnetic fields as your nerves are firing inside your brain. There are many uses of really high performance magnetometers. And I would say we all only scratched the surface. There are probably many, many other revolutionary uses out there. They're waiting for some creative team of scientists and engineers to unlock them.
Yeah, maybe that's actually an exciting place to start to wrap up. I mean, can you, we started looking back at the history. You mentioned that NV centers and this kind of technology is not new. It's been around for decades, but maybe there's, a more recent flurry activity because of all of the progress in quantum tech as a whole. But, if you want to, would you care to kind of speculate and maybe say what are these other new breakthroughs that may come on the horizon for NV centers?
Yeah, that's actually a great question. Now I have to think a bit more creatively and long term. Let's say when it comes to sensing, there hasn't been many companies in this space. I think this technology has been slowly but surely being developed in academic labs, and now it has been reaching points of sensitivity, operation, of kind of use that can be picked up from the academic lab and then turned into something that will be used in the real world by companies such as Sandbox, but many others as well. So for sensing, it's actually a very exciting time to be working on diamond NV centers. And I think really the best is to come because only recently there has been an uptick in the amount of startups, in the amount of even large companies considering and exploring the use of these sensors for magnetometry. Now, for other applications, I think that's even more exciting because this has been around. I mean, these are, let's say, computing and networking. These are very long-term projects, but there has also been a very high number of academic, but also industry applications, but maybe kind of attempts to bring this technology and improve it and make it useful for these particular applications as well. There is even a company trying to make quantum GPUs out of diamond, maybe not full quantum computers, but very specialized small scale computing units using room temperature diamond NV centers, which is also actually which could be groundbreaking as well. So there's really a lot of, this is what I maybe opened with. Once you have a really well understood quantum system that you know how to operate with, you can use it for many things. Maybe, I mean, conversely, the superconducting qubits used for quantum computers can also in some configuration used for sensing in the form of SQUIDs, superconducting detectors. So there is actually, once you have this quantum technology, you can use it for many things because the principles are very, very similar.
That's really interesting. And you got ahead of me there because I know that a lot of our audience is interested in quantum computing, and we've been taking pains to show that there's more to quantum than just quantum computers. And quantum sensing is like an amazing application for that. And I was going to ask you, like, what's stopping us from building a quantum computer out of diamond? That would look really cool, maybe. But then I had no idea that folks were already working on basically doing quantum computing with things like NV centers. I know we're almost out of time, but is there any other flavor that you can kind of add into that, or if you know about how those efforts are going?
Yeah, I mean, let's enter a bit speculative mode right now. I have not been part of these efforts, but maybe I can try to speculate. I would say that solid state, although it's really wonderful, it's also a bit dirty. There's also a lot of other impurities, other defects. You need in order to build a quantum computer, if you go down to, I think, the DiVincenzo criteria or whatever you want to use to benchmark your quantum computer, you really need to have a good initialization, readout, 2-qubit gates, coherence time as well. So you really need to have a perfect blend on multi kind of parameters for your qubit to be good for computing. Now, some qubits, like superconducting qubits, for example, are great. They have their own blend of parameters. Diamond comes with some strengths, but also some drawbacks. Scaling is a big one, right? Because for diamond, let's say for quantum computer, right now we know you need 1,000 logical qubits. So probably that means 1 million total qubits with like a huge error correction redundancy. It's very difficult to do this in diamond because it's very difficult to fabricate in diamond. One reason why it was so easy, or maybe why it's easier to scale other quantum technologies like superconducting, is because, and why, let's say, giants like Google and Intel are really leading the way, is because if you have a foundry for fabrication of your classical chips, with some tweaks, you can really scale up your quantum chips production. For diamond, these are still very small, difficult to implant or put in the proper exact places, and also difficult to interconnect because diamond also can eat up a lot of light as well. And your light is needed to basically communicate and transfer this. So I would say one huge part, and that's what I did my postdoc on, is fabrication of these super tiny nanostructures out of diamond. I think that's the difficulty of this is one big reason why these are difficult to make. But I think there are companies and teams and even some government institutions that are looking to work past that, because if you can crack the scalability of fabrication, then it really a whole new world opens up for you there.
Wow, that's really inspiring and super exciting that it kind of feels like we're on the cusp. Tai-Danae, what do you think?
No, exactly. I was going to say this is really fascinating. And thank you, Stefan, so much for breaking down some of these concepts for us and sharing your expertise and just the excitement around this kind of technology. Sandbox is super lucky to have you, and we're really lucky to have you on the podcast today. Thank you so much.
Thank you for having me. Yeah, absolutely.
And you teased quantum networking a little bit earlier, and I talked a little bit about that. And I know people have heard the term, and many people have heard the term quantum internet and things like that. So I think if you're up for it, maybe we'll have you back on a future episode to talk about those topics as well.
I would love that. Yeah.
Well, thanks so much for joining us.
Yeah. Thank you both.
Thanks. Okay. Wow. Well, we wanted some applied stuff to move from concept to application. And I think we got like a grand slam there, Tai-Danae. We talked about qubits. We talked about superposition. We talked about entanglement, all in like several different contexts around NV centers. How was that for you?
Yeah, that was fantastic. That was fantastic. I think you're exactly right. We asked for something and then we got what we asked for. That was excellent. Okay, several things come to mind. One, though, that really stood out to me, it's just what you said. We started this episode looking for an application of the three concepts we've talked about previously on the podcast. What was so interesting is that Stefan gave us one example that subsumed all three. So this thing about photon spin entanglement, you have your NV center and it's in a superposition of different spin states, which you can then entangle with a photon, so that depending on whether, this electron spin is like spin up, and I can't remember what Stefan said. If the electron is spin up, then, you have a photon. Or if it's spin down, then you don't have a photon. And then through that entanglement, you can then use that to send that photon over distances. And now you've entered into quantum communication. So we started talking about quantum sensing, but then it turns out that NV centers are also used in communication, which I didn't know. Which is not saying much because this is all new to me and exciting. But I thought that was really cool. That was more than what we asked for, I thought.
Yeah, no, I learned a ton during that. I've learned a lot about, I think that I've learned a lot about NV centers over the last year working at SandboxAQ, but I think it was literally just scratching the surface of that diamond and didn't even know exactly how those got built. I didn't know about the ion gun, for example, to be able to make very, very specific things. And that kind of resonated with me because there's these particle guns that I used to use back in grad school to shoot genes into plants. Something you and I can talk about some other time, maybe offline from the podcast. But there was a bunch that really spoke to me from my former biology career when talking with Stefan. And a lot of that came from when he was talking about a well-defined system and how NV centers and these different types of defects in diamonds are pretty well understood. And that's allowing them to be able to be used for all these different applications that you just mentioned. And that made me think about model systems a little bit in biology. So folks, even taking high school biology, you probably either read things about fruit flies or maybe Mendel and his peas, or Arabidopsis is a little plant that I used to work on. And all of these things are very well defined biological systems. So it's often in those well-defined biological systems that folks really start to learn about the genetics or about different interactions with ecology or different interactions between genes and the environment and things like that. So you can use this very well-defined system to learn a lot of new things that you're interested in potentially as a biologist or an ecologist or a chemist or something like that. And I see kind of the same thing happening here in quantum technology, where you have this well-defined system, NV centers in this case. And once you understand that system really well, you can start to play around with it in really deep ways and start to sort of probe how those things work and how different parts of quantum technology, quantum physics, and quantum mechanics actually come to play when you're working with them in real life. And again, that just seems like we're at the sort of tip of the diamond, tip of the iceberg, in really understanding how this system works. And I think that the knowledge that folks are getting out of this system will apply both to applications in NV centers, but clearly will also be much broader than that. And there's a lot of fundamental knowledge that's also coming out of NV centers and a lot of experiments that people can now do that were just based on concepts and theories outside of a particular framework, and then being able to map that framework onto this very well-known and well-defined system of NV centers, which is just incredibly exciting. Again, more evidence that we're on the sort of cutting edge of this technology.
Yeah, that's great. I love that connection that you made to biology. And yeah, I just got flashback to Mendel and his peas, which I haven't thought about for years. So that was good, Adam. In the kind of concepts that one needs to understand, and you have to understand the system well to know what are its pros or cons, or in which context should it best be used. Something Stefan brought up sort of briefly in our conversation is this idea about sensitivity, or whether you want to shield your qubit, or how much you want to shield your qubit from the outside, or maybe you don't want to because you want it to be receptive to incoming magnetic fields. But I mean, you kind of mentioned this. There are other applications where you really want to shield it from the surrounding environments. You don't want it to know what's going on the outside because that could actually be a disadvantage for a different application. And one of those applications is quantum computing. But like, what is quantum computing? What's a quantum computer? In which way is having, a delicate, sensitive qubit a bad thing in that application? I mean, this is like the other end of the spectrum. What are the answers to these questions? What are we talking about here? I mean, tune in next time, I think. Right, Adam?
I think so. Yeah, stay tuned.
All right, stay tuned, y'all, and we'll see you in the next episode.